Hi, this is Yuri from CodeVibers. Here, we build AI automation from scratch, develop AI tools for businesses, and run an educational academy. Today, no theory. We'll take a local node tool, intentionally break its dependency contract, identify the root cause, and get it running a real headless Chromium test. Subscribe to the channel, like the video, and hit the subscribe button. On screen, the full path, clean project, package.json and lockfile, executable preflight, expected red result, fix, npm CI, local server, browser smoke test, and final PNG artifact. By the end of this episode, we'll have not just a reminder to double check versions, but 4 commands you can add directly to your CI pipeline. A bad fixture must fail with a clear, understandable reason, while a good project must pass code checks, tests, and browser validation. I start with an isolated workspace. In package.json, I explicitly pin the package manager to npm v11, specify a Node.js version range from 22 to 27, and set a precise playwright version. Then I generate the lock file and run npm CI. The CI command is crucial here. It must not attempt to fix mismatches on the spot. If package.json and the lock file differ, the build should halt. After installation, I display the actual Node.js and npm versions, as well as the project's file structure. Now I'm writing an executable preflight. It compares root-level dev dependencies with entries in package.lock.json, validates the lock file format version v3, checks the Node.js version range, and verifies the pinned package manager. Each issue is assigned a stable error code along with the actual and expected values. Separately, I'm implementing a local server with a health endpoint and a browser-based smoke test. Chromium opens the page, clicks Run Diagnostics, waits for headless pass, and saves a full-screen screenshot. This is now a behavioral check, not just verifying that the process occupied the port. Running a unified demo. The first step uses a mismatched pair of files. Package.json requires playwright 160, while package.lock.json stores 1.61. Preflight returns exit code 2, and the orchestrator treats this failure as expected. Next, the same validator runs against the actual project and passes. Then, server, and just starts. Smoke waits for the health endpoint, launches Chromium, and executes the user action. Finally, the terminal prints not just server ready, but headless pass. I'm examining the red section separately. The lock mismatch error displays the package name, the required version, and the locked version. This is more helpful than a lengthy npm stack trace, as it immediately tells us the issue isn't in the application source code. The second edge test injects an unsupported Node.js 20 version, and the third removes the package manager field. All root causes are reproducible without network access or manually opening a browser. These are precisely the kinds of fixtures that protect the preflight check itself from yielding a false green status. Now I run node test. The first test accepts a synchronous contract. The second test must detect asynchronous dependencies. The third test blocks unsupported node versions, and the fourth checks for missing pinned npm dependencies. After the unit tests, I repeat the clean preflight. Here, the key is the pairing. Individual tests verify the validator's rules, while the browser smoke test confirms that the application actually loaded and executed a user action. I open the final artifact, smoke.png. It shows 3 independent checks. Lockfile is synchronized, Node is supported, and the browser script has completed. Adjacent to it, smoke.json stores the status, health response, and list of executed checks. This result can be attached to a pull request or saved as a CI artifact. If neither the PNG nor the JSON is generated, a green server log does not constitute proof that the interface is functioning. I'm moving this sequence into CI as dependent steps. First npm CI, then preflight, followed by unit tests, and finally browser smoke tests. Each step has its own exit code and artifact. A key detail, the bad fixture is run within the tests, not in the production job. Otherwise, the expected failure would halt the entire pipeline. The production preflight only runs against actual package.json and lockfile files. I verify the outcome with npm test, then run npm run demo. If preflight fails, is red, Chromium won't even start. Now I'm locking the result contract that the CI must persist. The bad JSON contains the finding code, package name, and the 2 compared versions. The preflight JSON confirms a clean project. The smoke JSON stores the health endpoint response and the 3 browser checks, while smoke PNG shows the rendered interface after the click. Do not consider the run successful based solely on the line server ready. Success requires all 4 tests to pass. Headless pass, the JSON report, and an existing smoke.png file with non-zero size. These are the files we attach to the pull request. Final order. Short and strict, lock the runtime, run npm CI, execute preflight checks, unit tests, and only then browser smoke tests. Do not replace npm CIS with a regular npm install in CI. Automatic lockfile updates mask the very class of errors we aim to detect. I'll add the project, themes, fixtures, and reports to the Academy article. Take any local web or AI tool, modify one version in the test fixture, and verify that the pipeline fails before the interface launches. Then restore the synchronous lock and require a headless screenshot. Subscribe to the channel, like the video, and stay tuned. We'll continue dissecting real-world builds and integrations.